Welcome to Cosmic Compass, where we navigate the mysteries of the universe together. Out there beyond the stars, we see every night lie the stories of planets, comets, and galaxies that shaped our past and may determine our future. Today, we're going to follow one spacecraft that set out to catch something no one had ever caught before the very dust of a comet. In that dust hidden for billions of years might lie answers to the most profound question of all: where did life come from? So let's embark on this journey and uncover how NASA's Stardust mission brought pieces of the cosmos back to Earth and what they revealed about the origins of life itself. Have you ever wondered where life truly began? Every atom inside us was once forged in the heart of a star. But what about the first building blocks of life? Could they have arrived here from the stars themselves, carried across the solar system on icy travelers? This is not just a poetic thought. It is a scientific question, one that became central to NASA's Stardust mission. At first, Stardust was not even designed to solve this mystery, but in its journey through space, it collected clues that brought us closer than ever to answering it. Today, let's explore how this remarkable spacecraft managed to capture dust from a comet, return it safely to Earth, and what its discoveries revealed about comets, the solar system, and perhaps even our origins. In the late 1990s, cometary science was still in its infancy. We had sent several probes to fly past comets, but what we knew about them was fragmentary and uncertain. Many scientists believed comets were interstellar visitors formed before the Sun itself, drifting for billions of years through the galaxy until captured by the Sun's gravity. If that theory were correct, then studying comet dust would give us access to grains older than the solar system, tiny samples of matter from other stars. All we needed was a way to reach one of these enigmatic objects, collect its dust, and bring it back home. But as with most things in space exploration, the challenge lay in speed and energy. Comets sweep through the inner solar system at up to 160,000 kilometers per hour. Even if a spacecraft could fly alongside one, any dust particle would still slam into the spacecraft at tens of thousands of kilometers per hour. Imagine trying to catch a bullet without shattering it. That was the near impossible task facing Stardust's engineers. How do you stop a particle travelling at 23,000 kilometers per hour without destroying it? The answer came in the form of one of the strangest materials ever invented, aerogel. Aerogel was first created in 1931, born from a curious bet between two scientists. The challenge was simple: could someone remove the liquid from a jelly without collapsing its structure? The solution was this ghostly material, 99% air, yet rigid enough to hold weight. Sometimes nicknamed frozen smoke, aerogel is light as a feather, translucent, and an excellent insulator. But for Stardust, its most important property was its ability to slow down particles gently. Instead of smashing into a solid wall, comet dust would enter the aerogel and carve a tiny track as it gradually lost speed. The particle would remain intact, suspended inside the material, as though caught in a soft cushion. Stardust carried a collector tray shaped like a tennis racket, lined with 90 blocks of aerogel each, a few centimeters thick. This device would unfold from the spacecraft and patiently wait for passing dust, cometary particles, as well as interstellar grains drifting through space. Once the collection was done, the samples would be sealed in a small capsule ready to be sent back to Earth. Stardust launched on February 7th, 1999, beginning a long 5-year journey across the solar system. Along the way, it passed by the asteroid Anne Frank, taking images as it sped past. But its true destination was Comet Wild 2. Scientists expected very little from this small, icy body. Some even described it in advance as a bland black potato. But on January 2004, as Stardust drew near, the images revealed something astonishing. Instead of a dull lump, Wild 2 was alive with activity. Towering pinnacles rose hundreds of meters above its surface. sheer cliffs cut into its crust. Gaping holes vented plumes of dust and gas into space, even from regions turned away from the sun. It was a far more dynamic world than anyone had predicted. Equally surprising was what scientists did not see craters. Unlike the moon Mars or most other airless bodies in the solar system, Wild 2's surface showed no scars from countless impacts. This suggested the comet's surface was constantly renewing itself, erasing evidence of collisions over relatively short timescales. Wild 2 was not a dead relic, it was active, changing, and very much alive. As Stardust swept past Wild 2, its aerogel collector was fully exposed. One by one, high-speed dust grains slammed into the aerogel, leaving tiny glowing trails within the ghostly blue material. Each track marked a successful capture, a preserved piece of the comet's story. These particles were precious cargo. Once sealed away, they awaited the most dangerous part of the mission, returning to Earth. In January 2006, the sample return capsule separated from the spacecraft and began its fiery plunge into Earth's atmosphere. The re-entry had to be perfect. If the angle was too shallow, the capsule would bounce off the atmosphere and vanish into space forever. Too steep, and it would burn to ash. For a few tense moments, all anyone could do was wait. Then, streaking across the sky above Utah, the capsule deployed its parachutes and landed gently in the desert. The mission had succeeded. Stardust had become the first spacecraft to return samples from beyond the moon. Back on Earth, scientists eagerly opened the capsule and began examining the precious grains. The results transformed our understanding of comets. First, the isotopic composition revealed something unexpected. Comet Wild 2 was not a visitor from another star system. Its material had formed in our own solar system. This discovery overturned earlier theories that comets were primordial wanderers from interstellar space. Even more surprising, the samples contained minerals that could only have formed under white-hot conditions: chondrules and calcium-aluminium inclusions, the same components found in asteroids near Jupiter and Mars. This meant that comets were not assembled purely from cold, distant ice. Instead, they contained material forged in fiery regions close to the young sun, later transported outward to the frozen edge of the solar system. In other words, comets are mixtures of both fire and ice. And then came the most profound discovery of all: the presence of glycine, a simple amino acid. Amino acids are the building blocks of proteins, the essential components of life as we know it. Finding glycine on a comet did not mean life existed there, but it strongly suggested that comets could have delivered these vital ingredients to Earth billions of years ago. Perhaps in the chaos of the early solar system, impacts from comets, like Wild 2, seeded our planet with the chemistry that made life possible. Think about that for a moment. The molecules that eventually became part of you might have first travelled through space inside an icy comet. After releasing its sample capsule, the Stardust spacecraft itself continued on. With fuel still available, it was redirected to fly past another comet, Tempel 1. This was especially valuable as NASA's earlier deep impact mission had struck Tempel 1 with a projectile but failed to capture all the desired data. Stardust filled in some of those gaps, extending its usefulness beyond the original plan. Eventually, however, the spacecraft's fuel ran out. In March 2011, after more than a decade of service, Stardust sent its final transmission, a signal across millions of kilometers, acknowledging the command that turned it off forever. The little spacecraft that had carried Stardust back to Earth fell silent, drifting endlessly in the void. What can we take from Stardust's mission? It showed us that comets are not simple frozen relics, but dynamic, complex bodies made of both hot and cold materials. It proved that some of the essential building blocks of life exist in space, carried within comets, that regularly crash into planets. The implications are profound. If life's raw ingredients came from comets here on Earth, could the same process have occurred elsewhere? Could comets be scattering the seeds of life across the galaxy wherever they strike a young habitable world? As we look outward across the universe, it becomes clear that studying comets is not just about understanding icy rocks. It is about understanding ourselves. The Stardust mission revealed that life's origins may truly lie in stardust, and perhaps so do our destinies. As Stardust showed us, even the smallest grains of dust can carry stories, billions of years old stories, that may explain how life began on our own world. It reminds us that when we study the universe, we are also studying ourselves. If you enjoyed this journey, make sure to like, share, and subscribe to Cosmic Compass, so together we can keep exploring the wonders of space. And let us know in the comments, do you think comets could be spreading the seeds of life across the galaxy? Until next time, keep looking up, because the cosmos always has more to reveal.